let us listen to the talk of Vesselin Gueorguiev about QAnon.
Yes, thank you very much. I would like to thank the organizers for the opportunity to give a talk about this research. The other motivation for this talk was actually to kind of pay the tribute to my mentors, Peter Raichev and Rusy Rusev, with whom I started my research in physics. Unfortunately, these were the two people that passed away, probably about many years ago. But they were like the eagles and the frogs we were discussing a few days ago, or more like the hummingbirds. They were a really good team where Peter had the vision, but Rusy was the one that would enjoy doing the calculations. And I remember when I was doing work on this research, he would go through many pages of printing output, verifying my calculations to make sure that he also understands and we have the correct results. We actually triple checked. I mean, it was me, him, and then we had a program that we wrote that would verify the calculations to make sure. And as you will see later, that the expressions are really kind of complicated. With this in mind, I will continue with basically the contents of my talk. Motivation, basically my background is physics, and this research was done many years ago. Basically, my motivation was understanding Hoff algebras because they have natural coproducts, which for physics point of view, I think is really important because when you go from one system to one particle, two particles, three particles, many-body system, the coproduct should help you with that. And in this respect, the many-body physics should be a good testing ground for these algebraic models. But then to be kind of specific problems to work on for my talk, I will go over a little bit about the Reshetikhin R matrix approach to quantum matrix groups, which back then I found it easier to understand compared to the other approaches of introducing the quantum algebras and Hoff algebras. So, of course, now at this point, AN, this is practically for physics point of view, is the unitary SUN or UN or SON algebras that you would usually have. But this is in terms of the classification of the semi-simple algebras. So then I'll go and just briefly explain, based on the Reshetikhin R matrix, how one can construct the Cartan-Weil basis of this algebra, and how to induce how to map the Hoff algebra structure in this case, and what are the mixed commutators in the algebra and the Borel subalgebras. Now, the next step is basically looking at boson realizations of these algebras, and these are actually Q bosons. But everything here in the talk, when you put Q to be 1, things would collapse, and this would get you back to the original standard algebraic formulations that are really interesting for physicists, like bosons representing interactions or quasi-particles in a system. Now, the key kind of tool that I use for constructing the embedding in my talk, which was a direct product of these two algebras to the bigger product. So effectively, this is UM tensor product with UN as a groups, giving you equivalently a subgroup of SUN times N. As Lie algebra, then it's a direct sum of the Lie algebras. So the boson realization is where we have proven this particular relationship, but then there's some potential obstacles whether this is possible in general or it's kind of construction dependent. But nevertheless, I will review quickly the Q boson algebra, the realization of the generators of the Q-deformed SON practically algebra, and then the Cartan-Chevalier and Cartan-Weil generators through the boson algebra. The tool that I use here is really the coproducts, just taking an n power of the coproduct to reach to the tensor product of space that has the right dimensions and structure that I need to start comparing the algebras. And then I'll show the specific embedding of the generators, and I'll point out what is a potential obstacle, whether if one can try to test this in general terms. And then conclusions and questions and answers. Of course, you're welcome actually to ask me questions during my talk. When I was preparing, I was anticipating this is kind of many years old material, so most of the things could be familiar, but then the same thing, it may not be familiar because people went and started studying other things and moved on. So motivation is like the physics, as I mentioned, when we go from classical mechanics to quantum mechanics, our observables become non-commutative objects, algebra of observables. But the important objects are really always operators. For example, the linear momentum of a particle, that's defined for one particle, but then we define it also well for many particles. And it's well-defined operator. The other thing is the spin of a particle. What is the angular momentum classifying particles by their spin? And again, we know what happens when you have a bunch of particles and how you add their spins to find what is their final spin. The other observable is isospin. Unlike the other two, the other two are having classical equivalents. The isospin is related to the symmetry between protons and neutron. That's practically realization of the weak interaction. And then again, example that is deeper into QCD quantum chromodynamics. If one wants to work with that, then the core quantum numbers, for example, they'll be related to SU3 realization of the strong interaction that describes the strong interaction. So going from one particle to two and more, because there's the question, how do you construct the Hamiltonian and any observables that you would like to consider in your system? And I know that the Hoff algebra should provide this kind of construction. Unfortunately, most of the physical cases, when we look at the Hilbert space of a multi-particle system, is just the product of the Hilbert spaces of the subsystems. And now the linear momentum, for example, would be just the addition of the linear momentum. But now in physics, usually 1, 2, and n, these are the labels. This is the first, second, third particle, and so on. But if you look at in terms of tensor algebra and in terms of the Hilbert space, this is actually saying, is it coming from the first component of the tensor product, the second component, and so on. And you can immediately see this is the nth coproduct applied to the generator of the linear momentum. Similar for the angular momentum, and the angular momentum, you can see it even better because angular momentum is related to the SU2 or SO3, the rotational group, and then automatically you know you have a kind of a very nice size group that you can work, practically commonly known. And then, of course, when you look at the generators, when you have a bunch of particles, this is, again, the coproduct of the angular momentum generators and the algebraic structure. The third thing is also the isospin is similar. Now, unfortunately, all these things actually give fuel to people in physics saying, well, where is your quantum deformation here? Because all they see in the experiments and all they need is only this. They don't need really the Q deformations. So if anyone knows actually a particular system where Q deformation could be showing and could be pointing to physicists why it's important practically, I would love to talk about this because that's what I'm trying to learn and find. The other reason is that basically, recently I'm working with people on quantum computing. And probably you heard me when I was asking yesterday about identifying the simple one-dimensional and higher dimension modules, because this could be having relevance to quantum computers and understanding quantum computing and how do you write, for example, using the coproducts to have a multitasking quantum computer. But I don't know, these are long-term things, but that's basically the motivation where actually the quantum groups are coming into play here. And specifically back to these two mentors that I had, there were some of the fathers of this interactive two-vector boson model. So in nuclear physics, my background, usually we use shells with quantum numbers. It could be related to the SU2 or SU3, that how you label your levels where you put the nucleons, protons and neutrons, and you can have other objects there. Generally, what is happening is that in nuclear physics, although QCD should be the way to describe it, when you go to more than 10, 12 nucleons, it becomes hard. The same way you should be able to understand chemistry from doing physics on atoms and molecules, but then you do only hydrogen and few light atoms, and then after that you just go and do chemistry. You don't try to derive it. But what is happening is you have a free Hamiltonian describing the system as free particles. There is an interaction, and this interaction actually breaks a larger symmetry. When they are free, for example, n particles distributed in the shelf very often is related to UN symmetry. In this model, they were considering two interacting vector bosons, and this was giving rise to U6 group symmetry. And there are different subgroups in this symmetry. Basically, you can branch into SU3 cross SU2, where SU2 would be related to the isospin, to the symmetry, is it proton or neutron, and SU3 would be related to the collective potential that would be built by the nucleons, and this collective potential would define kind of Elliott model, SU3 based. And then when you break the neutrons and protons, now you have neutrons, protons, and the collective potential where all the particles are moving. And this is one chain that would define the labels of your states of the system. You can have a different chain that would go directly from here, breaking into SU3 for protons and SU3 for neutrons, and then you have to go down to O3. Now, ultimately, you always get to O3, that's the rotational group, because that should be at least your final symmetry of your nucleus. Of course, now we know that there's a deformed nucleus that break this one too. I mean, you have to go to O2 because you have only rotational symmetry for them. But that was one of the chains. And then you can have a different one, which could be practically here you go to O6 as a subgroup of U6. So each of these chains give rise to different spectrum. For example, this one would give you vibrational spectra when you look at the excitation of the system. This would give you a rotational spectra, and this would give you something intermediate in between them. So what I'm talking now is just really this kind of trying to go this way and build a machinery to be able to formulate the subgroups. And the usual way that these Hamiltonians are created is that once you identify the subgroups, this is the second Casimir operator of the corresponding subalgebra, and with some strength. So this defines how much the system would be influenced by this particular subsymmetry. And you can have different interplays. So if we know what are the right choices to make for the subgroups, this will tell us how to construct these models. So now going to the R matrix, this was the motivation. Any questions about this from physics point of view or comments? Okay, so about the Hoff algebra relations among the generators. Again, the generators Lij, imagine this is matrix n by n, and I goes from 1 to n, and j goes from 1 to n. The co-multiplication is kind of standard one, where effectively you are breaking the usual multiplication of matrices. Then, because you have the unit which tells you how to embed your field, whether the complex numbers or real numbers, into your algebra, then you have the co-unit, which is a good thing to have. I mean, it's just the opposite process, and that's kind of easy also. It's kind of traditional to take it delta ij. What is default now is actually the relationships between this regular functions, so to speak, for the group. So they're defining the relationships between them, and the key thing is actually what is the R matrix. And this approach based on the inverse scattering problem, where this kind of mathematical constructions were considered. And in specific case, when we want to look at the specific, like SUN, SAN, for example, the determinant equal 1 would be expressed through this expression, and the unitary representation would add these constraints. And here, basically, L plus is upper triangular matrix, and L minus is effectively lower triangular matrix. But on the diagonal, you have non-zero elements. So this is general for all the types of matrices. You have to figure out what is the relevant R matrix, and then you can go and study the construction for this specific one. For the n-1 series, this is the R matrix that was introduced by Reshetikhin and his collaborators. And here, Eij, basically, this is a matrix with 0 everywhere except on the I row and j column. So that's only one where you have 1. And you see that the Q, that's parameter of deformation, is appearing now very nicely here in this expression. Now, the R matrix have to obey specific rules to be classified as R matrix, but I would not go in these details. For me, it's important to know what is the R matrix, and yeah. Yeah. So that there's relations between plus and minuses, and relations when with the same pluses and minuses. Yes, for this one. Okay. Yeah. So now when you use this matrix, then you can rewrite the expressions. And because we were going from standard Lie algebras now extending to Hoff algebras, we were looking at the commutators. That's why we wrote the expression in terms of commutators. But basically, this is effectively saying this is a quadratic relationship that you have to impose on this freely generated algebra from Lij's. And then basically here, this is saying that only when I is equal j, this term appears. And this term is only m is bigger than s. If it's not satisfying this condition, the term is not present. So this is in terms of the algebraic form. Then the next step is actually to go to the generators. In terms of Lie algebra generators, you have to do a mapping. And the mapping that we found useful for us was in this form. Basically, Yij, this would be now the generators that would correspond to the Q-deformed Lie algebra. Of course, you notice that there is additional term here with Hi and Aj. These are the Cartan elements. And these are very in the standard way, like you have the simple roots, and then you have Ij, the difference between two simple roots. And these are the Cartan generators that they commute. So these are the generators that help you build your basis, determine what are the eigen vectors of the algebra with respect to the Cartan generators. Then you have the plus and minus, the conjugate elements of the positive and negative roots, that when you commute them, you get back to the standard Cartan generator. but this is a Q number here, Q operator in terms of this expression. So this is kind of the step going towards Lie algebra, but notice that this here, the choice that is made, it could be a different one. One can take some additional function Fij, and this is important because later I'll show you that our construction, we get something like abstraction to be able to formulate this direct products in general. Maybe with the right choice here would be one solution of this problem. So after that, then one can go and derive what would be the commutators or also Q commutators. Actually, there is no Q commutators here. They will be on the next page. So when you look at, there's some zeros. Some of the standard commutators where these are two roots, and you combine them. So this is basically zero in the standard algebra. And it seems that this is kind of common theme. When you have in the standard algebra something that is zero, then often this will be accompanied by q minus 1, so that when you take the limit of q1, then these terms disappear. Now here is element that actually exists in the standard algebra. Basically, positive and negative root gives you another positive root, or positive and negative gives you a negative root. But when you get q equal 1, this disappears, and then you should be recovering the same commutation relations for the original algebra that are in the books. And similar for this one. Now, this last one is important because based on this, if you have simple roots from the Chevalier basis, you can generate the rest of the generators. Because here is ij, j, m. So from these two roots, because you have j in both, then you get im. And similar im positive root or negative root. So this is kind of the mixed commutators. The Borel subalgebras, these are actually within the positive and negative roots. And again, the first line is the standard expression we know from the Lie algebras, and it's not deforming. The second one actually gets Q deformation here. And I was very happy to hear from earlier talk by it was the earlier speaker, forgot her name, Pogorelski. Thank you. That basically, for us, when we were looking at this, Q was just a parameter in a weird expression. But now I understand that you can actually relate this Q with a character that you can have, and this becomes very nicely expressed that the Q commutators will pop up there. Then you have a bunch of zeros, and again, these are the quadratic terms that usually disappear. Now, the Q commutator in this work is defined this way. There are other cases where the Q commutator would be here Q minus first and Q here, I mean, depending on what the preference of the particular researcher is. But in general, that they should eventually be equivalent, a set of ideals that would define how you are factorizing, I mean, the algebra, the freely generated algebra. So these are the Borel subsets. And now, if I want to introduce the Hoff structure, now I go back original ones. Again, it stays the same for the Cartan generator. The co-unit is the same. The antipode becomes actually the same also for the Cartan generators. But for the other generators of the algebra, now there's a little bit modification. It comes with the value of the Q here. And then the coproduct basically becomes a little bit more complicated expression. But notice that in all these expressions, what matters are actually the relations between the indices. there is nothing which tells you, I mean, the range of the indices, you know it by when you start setting up the expressions, but in most of this, there is no specific choice. I mean, what is it? All that matters in these expressions are the relationships. That's what allowed us actually to do this calculation, because once you are not specifically checking for all different variations and you just try to figure out what are the different categories of indexes and relations, then you can prove the different expressions that you need to prove in general. And now for the antipodes, using the standard definition and the relationships in the Hoff algebra, then there's a nice expression for antipode which involves actually the previously known antipodes. So you start with the ones that are in the Chevalier basis, you compute their antipodes, and usually here, then for I and j to get it, then you need the previous few roots that are there that you need to use in the sum here to find what would be the antipode. But basically, we didn't use this in the later part of the calculations or anything else. So this is the structure in terms of Reshetikhian realization of this algebra. Any questions or comments? So then I can move to the Q boson algebra. So Q bosons are kind of almost like the bosons, at least there with respect to their number operator. And the rising and lowering is basically whether the number operator on the raising would give you a positive value, and if it's negative, then it means a lowering operator. Now, classically, you just have the commutator equal 1, but when you have a Q bosons, this is changing Q commutator, and you have here Q to the n for the algebra. So this is the one type of introducing the Q bosons. And then in a similar way, like in the standard realizations, you can define the Fock space of representation or module where you can act for a fixed number of particles. Now, of course, you can let the particles change within each of the subspecies, but you can have a module with a fixed number. This is relevant to nuclear physics, for example, because we know you have the total number of nucleons in a nucleus. Now, of course, a neutron can transform into a proton, but it doesn't change the total number of nucleons, and vice versa. So these are relevant representations. The only difference is here that actually a Q number appears in the denominator due to the Q commutation relations. Again, the dimensionality of the space is the same, and the total number of particles is just using the sum of the number of particles in each subspecies. Which way? BI. Oh, sorry, that's BI is AI. So this should be actually meaning annihilation. And yes, that's a good point. Because maybe this should have been B for bosons. I think that's where we were jumping between bosons and operators like A and B. But this is the same. B is A here. Sorry about that. I'll change it and then send a new slide. Good. Now, the Cartan-Chevalier generators, these are the simple roots of the Lie algebra. Basically, you have the simple Cartan generators and the simple positive and negative roots. Their boson realization is kind of very simple. It's A plus 1. You see, it's similar to what is in the Cartan generators. And the Cartan generators are just the difference between the two adjacent types of bosons. So in this respect, I mean, this is the standard boson realization of Lie algebra. Now, when you work with this, you can go back and rewrite actually whether you can re-express the number operator in terms of now the Cartan generators. And actually turn out that when you do this, you have the total number n, and you cannot actually express the total number n in terms of the Cartan generators. I think that's because usually there is a sum that gives you the sum of Cartan generators equals 0. And this you have to put it by hand in a boson realization. And this is another place where actually this creates obstacle later if you want to go back and rather than looking at boson realization for this expression into terms of the original generators of the algebras. Now, for the rest of the generators, basically using the previous expressions that I pointed out, like in the algebra here, was it this expression on top and this one, you can generate all the other elements of the algebra. And again, this expression, it seems kind of similar, overall simple. Usually you don't have the q to the power n, you just have the ai, aj as a boson realization of your generators. But in this q algebras, then this is showing up here in the realization. So we have the boson realizations, and now I'll go back to constructing actually my first proposition. This is based completely on the fact that we have the coproduct, and basically if I have the first one is K1, for example, and the second algebra is K2, then what I would need to do is on these generators I will apply K2 times the Hoff product, the coproduct, and this would give me a bunch of K2 generators, I mean K2 tensor products. The result is that this would become like K2 times K1 or K2, K1 times K2. But they would all live in practically two isomorphic tensor product spaces there. So the first here, the important thing is mu is related to the indices in the original algebra. S is a tensor index related to what is the tensor slots in the tensor products. In the Z and H, actually S, in this case, is actually the label for the generator within the corresponding algebra K2, for example. And then the low index mu is now index pointing to the location in the tensor products. So basically, because this is based on the coproducts, we are guaranteed that each of these operators here and here, after applying this coproduct the right way, and it doesn't matter actually what is the n, you would always get generators that would satisfy the same algebraic relations of the original algebra that you got. So if we do this, we can write the boson realization for the first copy and the second type algebra. So this is all expressed in the bosons, using the boson realization of these generators. And again, remember that here you have to be careful which generators are you looking at, but these indices of A, upper and lower, they are related to the structure of the boson algebra. So for example, if I'm looking at generator X tilde, the first one, then as I said, S would be pointing where in the tensor product am I looking at. And for example, I'll have a K2 tensor products and the mapping in this tensor space with the coproducts. For the Z, I'll have K1 copies. But then this K1 times K2, these both actually would be equivalent. And if you look at the algebraic relations between these copies or these guys, they would all satisfy the same expression. So this would be a boson realization of the boson algebra K1 times K2. So you have this Q bosons here with the tensor products that's formed here, these guys here, and these guys. All of them actually are equivalent. So now I'm loosely saying isomorphic here because there's other structures, but in terms of algebras, they are homomorphic there. So that's kind of the proof is relying on the construction of the generators. and then looking at the algebra. Now, the next part is actually this is the splitting construction effectively. Because here I had this algebra, and these two algebras would be the same. So I have first the equivalence of these two guys when I look at the algebraic relations, and I forget about the tensor products. But then if I look at this relation where I goes to mu s, and I'm just assuming that K2 would be smaller than K1, then I have a splitting. So it's similar to one of the speakers talk that was pointing, you have something where you try to break K1 here and K2 here, and that's how you label your indices. Now, in my case, I mean, I don't have remnants. I mean, there is nothing left. I'm just assuming that I'm interested in K2 times K1 algebra that's bigger. And that's probably another place where one can play with how one would split the operators in the big algebra and how this would go to the two subalgebras that are also equivalent, and they are related to a tensor products of Q-boson algebras. So now, because I had K1 and K2 already expressed in boson realizations, then I can claim that these two have expressions in this big algebra, boson algebra, this boson realization. And that's, the proof is basically by construction. I mean, here I have these generators. I know that they were forming the algebras before, and now I have it expressed in bosons and number particle generators. So by construction, I have this part. Now the next thing is basically saying that these two would commute with each other. So this is the tough part because then you have to compute, and this is specifically in the boson realization. So this was actually explained in the paper that we wrote back then. Any questions on this so far? So now, as I said, thing is that we can go back and rewrite the generators again in terms of the original generators. Here are the generators of this bigger UMN algebra. Now, the problem is that now there is obstruction here, I mean, whether this would work or not. Because for the boson realization, we got these extra terms in the copies of the second one, which is related to the total number operator. And it's not obvious now if you want to actually show that these two copies of M and N algebras are commuting with each other. The problem is that you don't have N. I mean, what is N in this sense? You need the boson realization. So, as I mentioned earlier, there could be few places where we can find with the right choice of the splitting function or the right choice of mapping between L and Y operators, we may actually be able to get something that doesn't involve the lambda here, this N operator. And then if it's expressed all in terms of the generators of the original algebras, then maybe we can verify whether they are really commuting or not. But this is open question in general. For the boson case, we kind of verified. And the other thing is lately, I was thinking that this could be related really to physical applications. If one looks at the coproduct as related to how you are doing measurement on a quantum system. Because this N is measuring all the bosons that are involved in the process. But of course, this is kind of difficult to really get an idea unless you look at specific example to figure out what is going on. So these are the generators. And basically, in conclusion, I'll just remind you the main things is, the proposition 4 is the main proposition of the paper saying that this realization of the K1 algebra through the coproducts acting K2 times on this one, and the same thing on these guys, we can get a realization through bosons within the big algebra, and over there will be really a direct product. They will be commuting in as algebras. Now, the key elements of this construction was the homomorphism mapping that was used from here to here, and then this is using the Q-boson algebra generators and the isomorphism between these three different types of Q-bosons algebras. So this is the one that is effectively utilized to verify that these copies in boson realization would commute. With this, I would like to thank you for your attention. And if you want to look at some of the references, I will put it here. Any questions?
Any questions? Or comments? So let's start with
Thank you.